Okay, let's talk about metallic bonding. So next job, strength of metallic bonding for 27.2. By the end of this assignment, you should be able to look at a period on the periodic table going all the way along and explain some properties that you see there. So we'll start doing that today. That is going to link to the type of bonding you see here. So we talked about this a little bit in assignment 1.1, but you talked about it loads at GCSE. So I'm going to spend very little time on this. Ionic bonding, your metal, as you know, wants to form a full outer shell by losing an electron. Your non-metal, as you know, wants to gain a full outer shell by gaining an electron. You get the idea. And that leaves us with a full outer shell. This was working earlier. Full outer shell on the metal and full outer shell on non-metal. That becomes positive, that becomes negative. The two are going to be attracted to one another. Now that students are usually very confident with that bit so far. The important thing is the result of this and what it means for the structure. So we're talking a lot about structure in this topic. We're talking about how are all of the many millions of atoms assembled. And that's obviously going to be quite different to how two atoms are assembled. Okay, so how all the many, many ions that we get from ionic bonding are organized? Well, that's this. Okay, this is one representation of it, a 3D lattice, a regularly repeating solid where everything is nicely arranged so that it's got all those nice attractions that it needs. So the attractions between negatives and positives are often the things that hold our structures together. That's ionic for you. If you're not sure what's going on there, look it up on BBC Bitesize or something. Metallic is actually slightly more complicated, and students tend to have a bit more difficulty with this one because there's a bit more to it that we need to talk about. So this time I've got the same metal as we had a moment ago. It still wants to have a full outer shell, and it's still going to do that by losing some electrons. So let's take this one, for example. That electron is just going to wander off, and we don't have a shell there anymore. And so now we have, as you will remember, what we call a delocalized electron, which can nip all about and go all about the solid. Okay. That is going to allow us to be attracted to different atoms in the solid. And importantly, each atom is going to do that. We're going to lose an electron from each atom, and we're going to have a load of delocalized electrons in the solid. So that leaves us, they're irregularly arranged, doesn't really matter. I've managed to make them look regular. That's going to leave us, let's see if this works, with a 1+ charge on all of the atoms, which they become 1+ ions. That's important. You wouldn't get the mark for saying atom. If they've got 1+ charge, they must be 1+ ions. There we are. And the reason this metallic structure is held together is the attraction between the positively charged ions and the delocalized electrons. Again, I don't want anyone writing negative ions for this. There are no negative ions to speak of. These things are attracted to one another because that's negative, that's positive. And the sea of delocalized electrons gives us our properties that we like the conductivity and so on. Okay, again, look on Bitesize if that didn't make sense. That should be GCSE. However, as I said, we need to be able to talk about what's going on this thing, and we're going to look at sodium, magnesium, and aluminium. We're going to look at the strength of the metallic bonds these things form. So there they are. You'll see I've changed the way I'm drawing them slightly. Sorry about that. Skip to that. So sodium, magnesium, aluminium. These are the outer shells I've shown here, the outer shell electrons. Now, what we need to be aware of is that when these ions form, we've just done the sodium case, we've just removed that one. So that's gone off and is delocalizing in this rest of the solid without that. So we're left with the sodium. In the magnesium case, we're going to lose 2 of them. So there they go. Off to delocalize with other magnesiums. And in the aluminium case, we've lost 3 of them. 1, 2, 3. Now this is important. Desktop's frozen. This is important because we need to know how many electrons we lost there. Come on. Because that is going to have an effect on the charge we get. In the one we lost 3 electrons of, we get a 3 plus charge, and a 2 plus charge, and a 1 plus charge. Now, this aluminium here has what we call a higher charge density. It's got a very high charge. The electrons in its outer shell are going to be very, very attracted to that nucleus. So crucially, they're going to squeeze in, like we saw in the last video. Okay, so the 3 plus ion is smaller than the 2 plus. And the 2 plus is smaller than the 1 plus. Okay. That means that the distance, as these electrons approach here, that means the distance is less as well between that and the nucleus. But the key thing is, if it's a 3 plus charge, it's going to be very strongly attracted. So this electron would want to go in a strong attraction close to those aluminiums, if it could. And you remember, we lost 3 from the aluminium, 2 from the magnesium, 1 from the sodium. So, as I hinted at the start of the video, we are going to be looking at the strength of the bonding in these different metals. Well, there's the sodium. I'll zoom in a bit now. 1 plus, this is how we draw them actually. This is a good way of drawing them, not too far apart, clearly a solid. Here's our 1 plus ions and our delocalized electrons all buzzing around them. And the 1 plus ions are big. There's not a very strong attraction to them, and we've only got 6 electrons to be attracted to. I've drawn 6 ions, 1 electron per ion because of what I talked about in the last slide. So 6 fairly weak interactions there, not a great attraction. Go over to aluminium. Well, you can do the maths on this one, I hope. 18 delocalized electrons, and the attraction of the ions towards them is much stronger because these are 3 plus ions. If the attraction is strong, the melting point should also be high, because that means it's hard. It's hard to persuade this 3 plus ion to leave. That's what we need to do for melting. Relatively easier to persuade this 1 plus ion to leave, because it's got fewer and weaker attractions to the other things in the solid.